So this is an example of a covariance calculation using Excel, using a priori probabilities. So rather than just using observations and data, we've got the actual probabilities of all the different x and y's occurring, and we calculate it from there. So notice I've got two variables here. I've got salary and benefits. So the idea here is that when wages are good, maybe benefits are also good, but those two things don't necessarily move in concert. So for example, if the legislature passes legislation for restricting collective bargaining by public employees and takes away some of their benefits, well, that's going to make benefits move differently than salary would. Whereas if, say, a union were able to push for higher salary while maintaining the benefits, that would move in a different direction. So I've got this example here. I've got salary and benefits, and I've got the probabilities of all of these three different things occurring for both, right? Booms in benefits, average salary, that sort of thing. So, and you can kind of see just by looking at this that they tend to move together a little bit. So when it's bad for benefits, it's bad for salary in this example. You have a 20% of those happening, a 30% chance of being average in both, 20% chance of it being a boom, and then 15% on both sides of the off entries. So it's possible to have a boom in benefits and a bust in salary, but not as likely. So these are the probabilities of all of these things happening jointly. Okay. In order to do the calculations we need the marginal probability for all these states. So if I have a 20% chance of bust for both, 5 for average and bust, and 5 for boom and bust, that means that my total for a bust salary is 30%. And I'll get the same thing here for average and boom, and similarly I will do benefits here. So the marginal probabilities are 30 for bust, 30 for boom, and 40 for average, both for benefits and salary. Now notice for the covariance calculation, we need the actual values of x and y and not just the chance that they show up. So I have these 30, 35, 40, that's the salary, and then 8, 12, and 18,000 for the dollar value of benefits. Another number we're going to need for our calculations is expected salary and expected benefits. So I will use the formula sum of x minus expected x. That's the definition of expectation. Oops, excuse me, sum of x times probability of x. Sorry. Times probability of x. The other one is for variance. Probability of x. And find the expectation of x. So probability times x summed up. Probability times x plus probability times x. So there's our expected salary. That makes sense, right? If these are symmetric, 30 is 5,000 less, this is 5,000 more, so we get 35 on average. This is 4 under and 6 up, so it's going to be a different number. Equals this, probability times y plus probability times y plus probability times y. You get 12,006. Okay, the definition of covariance is a sum of things that look like this. X minus expected x times y minus expected y and then times the probability of x and y. So I'm going to follow that exact formula and entering the value for these various cells. So I'm going to have an X. So for the entire bust column, I want X to be 30,000. So the bust column is E, so I'm going to lock in E. That's X. Expected value of X is here. Lock that in. Then I'm going to multiply by Y. So if I'm here in the bust state, I have 30,000 in salary and I have 8,000 in benefits. 8,000, and we want to make sure that this stays in column I, and this should actually be row 39. Right? We want it to be able to move from 30, 35 to 40, so it needs to stay in row 39 but not move up and down. Whereas this one needs to stay in column I, and then subtract minus expected Y, that's expected Y, lock it in, and then times the probability of X and Y, which given the contingency table we have is here. So that is our value for that cell, and we need to add up all the combinations of X and Y, which is 9 different things. So fill down 3, fill over 3. Covariance is the sum of all those things. So sum of those. This number here is the covariance. Now if we're interested in the correlation coefficient, we can do the covariance divided by the 2 standard deviations. So let's do that now. So we need to calculate the variance of X and the variance of Y. So the variance of X is defined to be the sum of, it's the covariance of X with itself. So we replace this with just a squared, and then X and Y is just X and X, and the chance of X and X is just X. Okay, so this is these are covariance calculations here. And now we'll want to do our variance of X calculation, which is equal to X minus expected X, the quantity squared, times the probability of that X. We want to lock that in. And then add those. Right, and for Y, we want Y minus the expected Y, quantity squared, times the probability of Y. Drag that down, and so. Okay, so this is the variance of X, this is the variance of Y. I take the square root, I get the standard deviation of X. And if I take the square root, I get the standard deviation of Y. Which means the correlation coefficient is equal to the covariance divided by standard deviation of X times standard deviation of Y. Giving us a correlation coefficient of 0.496. Which means that these two quantities, this is positive and fairly large, so they move together. So when salary is high, benefits tend to be high, and when salary is low, benefits tend to be low. And as you look, you can see this is true, right? We move from 30 to 40 as we move from 8 to 18, but not perfectly. We have these off diagonal elements. So that sometimes we're busting when it's a boom, and sometimes we're booming when it's a bust. But generally, they will stick together. So that is a full covariance calculation with expectations and variances and ultimately the correlation coefficient.